Yeah, so last Monday we started just talking about some of the ongoing research in my lab with the goal of giving you a flavor of what security research looks like, and also to to give you an overview of some of the ongoing work. So in case you're interested in doing research in the area, you can follow up with me. So in the last lecture, we talked about one of the, we started discussing some of the ongoing research in techniques for, primarily software vulnerability mitigation by, instrumenting binaries. And we talked about one particular problem, which is how do you, you know, deal with the complexity of modern instruction sets that have a very large number of instructions. The instructions change all the time, and in addition, the instructions themselves have very complex semantics. And I talked about an interesting way that one of my students developed, which is based on using compilers to help in extracting the semantics of instructions, and then using this extracted semantics for doing binary analysis or binary instrumentation. So that brings us to the question of instrumentation, which we have discussed before in this course. And one of the, we pointed out that instrumentation of binaries is quite a challenging problem. And, we primarily discussed dynamic instrumentation techniques. And these dynamic instrumentation techniques are generally quite robust, whereas if you try to statically do the instrumentation, which means that before the program starts executing, you instrument all of the code, then that faces many challenges. And and that's exactly why it's a topic of research and something that we have been working on for the past several years. And in fact, a lot of the work that I'm going to talk about today is done by students that have taken the course in the last 6-7 years. So we have talked about in general terms about some of the challenges, such as disassembling itself is quite difficult. Disassemblers can get confused with complex binary code. And then the second challenge is that if you start instrumenting code, then there are many problems that are introduced, such as how do you fix up targets of indirect control flow, because if you recall, this is sort of one of the main reasons why dynamic instrumentation techniques are good, because when a indirect control flow transfer takes place at runtime, that's when you know what is the target address. And then because instrumentation changes the addresses of existing code, anytime the code jumps to some location, the intended code is not there. It's at a different place because you had to instrument, and that caused the code size to increase. So a function that was at location 100 may now be at location 150. And so this sort of fix up has to be done. And unfortunately, it's difficult to do this fix up when you are working on just the binary, because the number 100 doesn't tell you whether it's an integer 100 or whether it is an address 100. And this is why with dynamic instrumentation, you have the advantage that when the program itself uses 100 as a target, then you know that it is supposed to be a code address. And at that time, you can say, hey, whatever code was there at 100 now is at 150, and I'm going to jump to that, right? So that's sort of one of the challenges in static instrumentation. And there are a number of other challenges, and how do you deal with all of that? and how do you make sure that the code will work correctly after instrumentation. That's a second challenge. And the third challenge is that you want your instrumentation to be secure, because your goal is in the context of security. So you want to make sure that any instrumentation you put is not bypassed. And we saw examples of this when we were discussing software fault isolation and control flow integrity, where malicious code can try to subvert the instrumentation by essentially jumping past the checks. And we discussed how that needs to be handled. And so if you want to do instrumentation in general, you need to think about how do you make sure that things are secure. And so this is something that we looked at, and we found that, in fact, you can get accurate disassembly by using a simple linear disassembly technique combined with some kind of error detection and error correction. You can find the details in our paper, but the main point is that by and large, most of today's compilers don't put data in the middle of code. And if you recall, the biggest problem for linear disassembly is that it can be confused by data in the midst of code. So if you have binary code that rarely has code in the middle of data in the middle of code, then it makes sense to start with linear disassembly. And in the few cases where it gets into trouble, what we do is we have techniques for detecting these errors and correcting them. And then we already talked about this problem of finding code pointers and fixing them up. What we did is that just like dynamic binary instrumentation, we decided to do just-in-time translation just before the code pointer is used as a target. We do the translation to the new location of that code, and then that gives us the same kind of robustness we get with dynamic instrumentation. And we also have ways to we also showed that again, by using control flow integrity, you can make sure that any instrumentation that you add cannot be bypassed. So you can find this paper on my lab's website. It's I guess 7 years now, so it's been some time. And because we did it about some time ago, so the work was done on 32-bit binaries, right? So which was the prevailing platform at that point. And we showed that we can take large amounts of code and be able to instrument them and have pretty complex applications like Firefox and so on work correctly. We also showed that unlike dynamic techniques, which have a very high performance overheads, the static technique has actually quite low overheads. So we also showed that the instrumentation is secure and so on. So most recently, what we have been working on is, in fact, a couple of students who took this course with me 2 years ago, which was the last time I offered this course, started, thinking about, okay, what is it that we can do to further improve, the results that we got, 6 or 7 years ago. And one of the questions is, as we said, there is this translation of code pointers that is done at runtime, which although it is not as expensive as dynamic binary instrumentation techniques, it is still a significant or non-trivial overhead of 10%. And so the students asked whether we can further improve on that. And it turns out that when we go to 64-bit platforms, in fact, we have more help from the compilers to identify code pointers, and as such, it is possible to identify and translate these code pointers at instrumentation time, and therefore you can avoid this runtime translation overhead completely. And so as a result, you can instrument binary code, and there will be no particular overhead at all. So that's the most recent work. We showed that by using information that's already available in 64-bit binaries, together with some improved binary analysis techniques that we developed, by combining the two, we are able to get rid of this address translation step, which is a significant source of overhead, and also significant source of runtime complexity, and both of that we avoided. And so the summary is that we can take code written in any source code, any source language, because again we are working on binaries, so the source code really doesn't matter. And we can also work with binaries produced by different compilers, as well as handwritten assembly code. And the system itself is quite robust and is able to deal with a lot of complex code while essentially producing zero overhead. Again, zero overhead means that you didn't really try to add any significant runtime checks, because if you add instrumentation that requires a lot of runtime checks, then of course the added instrumentation will always have overhead. So when we say zero overhead here, what we mean is that the infrastructure itself does not produce any overhead. It's the actual instrumentation that you decide to add. And so we have specifically applied this to fine-grained code randomization. So this is one of the techniques we discussed when we were discussing memory corruption vulnerabilities and attacks such as ROP, and how you can make ROP difficult by doing fine-grained randomization of code. And one of the key questions is whether you can do fine-grained overhead with very low overheads, and that's what we are able to do using this technique. So let me stop here and see if there are any questions on either this topic or anything else we covered in the last lecture or the one before. Any questions about the midterm or the quizzes or anything else?
I have a question, actually. Yeah. This might be a refresher of material. When you're doing this static binary instrumentation, what's the threat model for the attacker here?
So that's a very good question, right? So because this is the thing that we often get mixed up about. In the examples you are given, right? So you were, the applications the instrumentation you did, for instance, if you want to do, you know, let's say if you want to print system calls, right? So then the threat model, the expectation there is that even if the code is malicious, you should be able to, you know, this should work correctly, right? So the threat model for that example is that it should work with, you know, code containing vulnerabilities or as well as malicious code. So to a large extent, most binary instrumentation techniques should work with, you know, either benign software or, you know, untrusted code. This doesn't mean that, you know, the tool will always succeed with malicious code, but the important point is that if you're developing a security instrumentation, then you want to make sure that if the code behaves differently from what you expect, you know, it shouldn't be able to evade your defense.
Then I guess my follow-up question would be, and maybe I missed this in your slides, but what was the solution to the attacker potentially injecting data in the static binary?
Right. So the question is whether the instrumentation, there is no instrumentation technique that's going to necessarily work on all code. The question is whether the attacker can silently escape being instrumented, or the tool will complain that the binary you know, does not satisfy certain conditions, and therefore it fails to instrument it. So one of the things that I pointed out here is about you know, secure instrumentation, and so secure instrumentation here means that if the code under certain assumptions, if the code you know, follows certain assumptions, then it will be securely instrumented. Otherwise, there will be a compile time or runtime failure, right? So this is the meaning of what secure means here. Does that help?
It does. Thank you.
Yeah. So that's yeah. So almost none of the tools will tell you that you know, it can so the problem is that if you if you're using these tools to defend your system, your goal is to make sure that you know, malicious code cannot evade your defenses, right? Your system may break when you try to do something to malicious code, but it should certainly not be the case that malicious code can silently bypass your policy. That's the thing that you want to avoid. Anything else? I guess we are getting close to the end of the semester, so the energy level has dropped. But I guess you know, you need to save all your energy for the next few days, because you know, I guess this is the first finals for most people, and so you know, you need to get this done quickly. So okay, so let's let me go on to talk about a second research project that's ongoing, which relates to intrusion detection, and in particular, you know, earlier on, I showed you this model of sophisticated attack campaigns where attackers break into an enterprise and stay hidden for weeks or months, and you know, and their goal is to you know, carry out damage over that time, or more likely they are interested in this, high value asset acquisition, which typically is some kind of information such as, secrets in a company, trade secrets, financial information, account information, things like that. And so, as you can see in the news, very often these attacks are not detected for a very long time. And the research that we have been carrying out is on how do you really make it, make it possible to identify these attacks as they are going on, right? So the technical challenges we can very quickly summarize as there are two technical challenges. One is what we call as a needle in a haystack problem, and this is the problem that in a large enterprise there is a lot that's going on, and so there are a large number of events, security relevant events that are taking place, and these need to be logged and analyzed. And so you can easily end up with a situation where you have billions of events per day that you need to analyze. And the question is, when you look through such a large collection of events, how do you know, which ones are problematic? Because, very often, not even 1 in a million event is an attack, right? So how do you, tune into that small fraction without getting lost in the background activity? And the second problem is, what we call as connecting the dots. Because if you simply say there is some, alarm going off here and some other alarm going off there, the analyst who is looking at all these alarms is not able to piece together all of these alarms that are going on in different places. And this is a particular problem, not only because these alarms are in different places, but also because there are a large number of alarms. And so the analyst doesn't know which of these alarms are false positives, which are really indicative of attacker activity. And that's part of the problem. The second problem is that even if they realize that something is part of an attacker activity, they just don't have any visibility into what happens next. So what is the attacker doing? So because attacks are always happening, right? So it's not the case that attacks are so rare that the moment you detect an attack, you can shut down the system and start, investigating the problem. The attacks are going on all the time. Every day there are many attacks. Most of them don't really succeed, or they succeed in the first step, but the attacker is not able to get too far. And so most of the time these attacks are, don't require the system to be shut down or the services to be interrupted. And so, so there is a lot of analysts generally are reluctant to, do anything that brings down the service. So they are, when they see alarms, they have to understand what is the impact of these alarms. And without knowing the impact and without knowing what the game plan for the attacker is, they are not able to, decide what to do next. And so what we want to do is to be able to, connect together the pieces so that the pieces of the puzzle come together in a way that the analyst can actually see what's going on. So let me give you an example here for how these sort of sophisticated attacks work. And I'm obviously using the simplest possible example that I can create to give you a flavor of how attackers have exploits and how they chain these exploits to achieve something to achieve a goal that they have. So the attacker's goal here is, they want to insert a backdoor into some software vendors, vendor software, right? Because, well, attackers wants to get their malware, installed on many machines, but obviously most people won't be downloading, attackers malware and installing that, right? So the attacker needs some way to get their malware into a large number of systems, and one way to do this is if they can poison some trusted vendors software repository. So that's what the attacker is trying to do. So to simplify the picture, let's assume that the software vendor does everything on a single host, right? This is just to simplify the example. So let's say that one of the developers are maybe the sysadmin on this machine. Let's say his name is Bob. He is doing some research on the internet, and while doing this, they visit a website, and that website contains an exploit that compromises their browser. And at that point, what happens is that so the Firefox gets compromised and it starts running malware. And this malware does two things. One is it saves a binary file called crt1.o in Bob's home directory. And it also modifies Bob's bashrc file. And the reason why it does it is because ultimately, in order for the attack to work, this binary crt1.o has to be installed in a system directory, right? In particular, it has to be installed in something like a /lib or something like that. But in order to write into that directory, you need root privilege. And you can imagine that Bob won't be running Firefox as root. So even though Firefox has been compromised, it cannot write directly into that directory. So what the attacker does is the attacker wants to essentially put a trap into bashrc and then wait until Bob uses sudo to, say, install some software, right? At that point, Bob will acquire root privilege, and the goal of the attacker is to use the root privilege that Bob has at that point to copy this file into the right directory. Okay, so that's what happens here. So when Bob uses sudo to install some software, maybe by using apt-get, sudo has been redefined so that in addition to doing what Bob wants, it also copies this file over to the /lib directory. And now it has root privilege, so this can be done. And then at this point, Bob is done. And later on, another developer, Alice, comes in to build the software. And at that point, the compiler compiles their source code. Let's just call it, it's called test.c. And then the linker produces an executable called home Alice test. And one of the things that loader does is it copies the code from this /lib/crt1.o. By the way, that crt1 stands for C runtime. Okay, so it's a standard library binary that the compilers basically copy this code into every executable that they produce. So this is why the attacker is targeting this binary. If they can replace the standard crt1.o with a binary that contains their malware, then every binary that's produced by a compiler is going to have the attacker's malware, right? So that's the goal. And now when Alice built her source code, then this test program contains the attacker's malware. And from now on, If the attacker runs the code, then you can then the I'm sorry, if anybody runs this code, whether it is Alice or when this software piece of software is installed on your user's machine, and when it is run there, in both cases, now the attacker's malware is there and it's able to run. And so the attacker has got their malware into the system, and you can imagine that the malware may, in fact, call back, connect back to the attacker. You can see that this address and this address are basically the same, right? So this is the attacker's website, and it's going to connect back to the attacker's website. So the attacker can say, take over control of this software. So any questions? So this is an example of how, typically the attackers cannot do what they want in one shot, and so they have to essentially break their attack into pieces, and some of the pieces may actually require an inside benign user activity in order to in fact make the whole attack come together, right? So here there is this benign activity of Bob, which was this benign activity was hijacked by the attacker. And again, another benign activity is the compilation done by Alice. And another benign activity is when Alice runs this code. All of these benign user activities have been hijacked by the attacker using this one step in their in the whole process. So this is sort of the system that we have. So we have these event streams coming in, and from the event stream we construct a dependence graph. Dependence graph basically captures how the dependencies in the system. So let's say you download a file and then you run it, then there is a dependence between the download action and the code that runs. Similarly, if this code writes another file, and if that file is read by another process, once again there is a dependency. And the idea here is that when the way to trace what's going on in an attack like this is to trace the dependencies, because here is the file that is produced when Firefox is compromised. Then you have a dependency from that to copy, which produces this. So if you follow the dependency from the initial attack, then you are able to largely uncover what the attack is. And this is sort of the basic idea behind constructing this kind of a dependency graph and performing an analysis on the dependency graph in order to detect the attack. So to detect the attacks, we use this dependence information together with some policies for detecting attacks. So in particular, we define something called trustworthiness, and in particular focus on trustworthiness of code, right? So code that's coming from, say, your vendor would be something that you would treat as trustworthy, but code that's coming from some unknown site, for instance, code, anything that's you download from an unknown website such as this would be considered untrusted. And the idea is to follow how this data that you download from unknown places is used. If it is ever used as a code, then that tells you that there is potentially a problem, because it could be malware, and then you could be getting compromised. And based on how this untrusted content is used, there are several policies for detecting attacks. The most common one being execution of untrusted code. So anytime something is some untrusted piece of code is executed, then you have an alarm. Another example is what is called suspicious modification, where something a benign file on the system is being overwritten by something that's coming from an untrusted site, and that could be an indication of an attack. Another thing that we commonly see is when some file is downloaded and it's made executable, then that's again a potential sign of an attack, and that also will cause alarms to go off in our system. And once these alarms go off, then what we do is we basically so we can show the example over here. So for instance, so here is an example where suspicious modification is detected because bashrc is normally a benign file. It should have been changed only by the user or as a result of system updates that are coming from a trusted source. But when it is modified as a result of by Firefox, which is communicating with an untrusted site, then that's a reason to trigger an alarm that potentially something is going on. And a second type of alarm that may be detected is when this file is copied over into the /lib directory. And once again, you can see that some untrusted file, untrusted content is overwriting a benign or a trusted file. And then, when the compiler produces an executable that is derived from this untrusted file, and ultimately when it makes that binary executable, then once again, this untrusted execution preparation alarm will go off. And finally, when this untrusted code is executed, then you'll have untrusted execution alarm. And so it's these alarms that basically cause us to analyze what's going on in the system and then build a picture of what is going on. And once an alarm goes off, there are two things that happen. One is called entry point identification or backward analysis. So what we do is, given this kind of a graph, you can see it here. So what we do is we start from one of the alarms. Let's say we start with the untrusted execution alarm, and then we travel backwards following these dependencies until we reach a network entry point, because the assumption is that attacks would typically come in through the network. And then this kind of backward analysis in this dependence graph will tell us the entry point of the attack. And the reason why we want to find the entry point is because we want to go back and then say, okay, now that we know the entry point, let's go forward from there so that we can find everything that the attacker has done. And that's what we do in this next phase, which we call as forward analysis. So all these slides are showing is basically they're animating how the backward analysis work. So once we find the entry point, then the next thing we do is forward analysis, which is intended to identify what did the attacker do once they got into the system. And so basically what we do is we look forward from here, and we follow all of these arrows going forward, and we construct this picture, right? And you can see there are red arrows that show events that have a dependency on this untrusted website, and then there are green arrows which have no such dependency. And so the idea is that we ultimately produce a graph that only captures these red arrows, and then you have a picture of what the attack is without having to worry about the benign activity that really didn't have anything to do with this. Okay, and once again, this is showing the animation of the forward analysis. So let me just give you stop by quickly get to the conclusion to show what this kind of analysis produces, because again, remember, the goal is to construct is to identify these alarms and then connect them together so that the analyst can see is the whole attack scenario, right? And they can therefore understand exactly what is going on, and have a sort of a high level picture of what goes on. So in order to see how well it works, so we this research was done as part of a research program sponsored by DARPA, which stands for Defense Advanced Research Projects Agency. If you haven't heard about DARPA, then the one-line description is that they say, our research created the internet, right? So that's what they talk about. So one of the things that DARPA does is that in addition to asking people to carry out research, they give them the tools for evaluation. So what they did was, in this case, they created basically, they commissioned a red team to carry out a large number of attacks, and then the goal for us is to essentially just look at the data that comes from these attacks, right? So if you recall the picture of our system, right? So we have this, I'm sorry, went too far. Yeah, so so there are these event streams that comes in. So what we are given is that as the attacks go on, the logging systems are enabled, so these events are logged, and then we are given this event log, and then we need to basically take these logs and investigate what's going on, and come up with a picture of what went on. So a typical in this example, the log contained in the range of about 1 million events, maybe 100,000 to 1 million events. I don't remember exactly. And the idea is, you need to find the attack, which typically, is, hardly 50 to 100, events in there. So anywhere between 1,000th to 1/10,000th is really the attack. So so by doing this kind of analysis, where we have these, we construct these dependence graph, we have these policies for generating alarms, and then we have this analysis, backward analysis and forward analysis to construct the this kind of a graph that shows the attacker activity. This is the result that's produced by our system. And what it kind of shows here, let's just go through this quickly, is that, like the example we had, everything starts off with some kind of an exploit of Firefox. And this exploit causes some binary to be written on the system. So this is happening on a Windows machine, which is why you have all these backslashes instead of forward slashes in the file names. So I guess the attacker tried to make the binary look kind of legitimate, which is why they called it Mozilla Nightly. So this binary gets downloaded, and at some point it runs, and when it runs, it looks like it connects back to the attacker. So we can surmise at this point that perhaps this malware is a command and control kind of malware. It gives basically a remote login for the attacker, so they can interactively probe what's going on in the system. They can download new malware and run it, gather data, exfiltrate this data back to themselves, and so on. So so what some of the things that you notice here is that it is downloading a program called photosnap.exe. You can imagine, of course, just looking at the logs, you can't figure out exactly what this program does, but you can surmise that maybe it's taking pictures using the camera, and then but you can also see that it creates a picture file, and this picture file is being read back by this malware and then exfiltrated, sent back to the attacker's website. And similarly out here, you see that the attacker comes in and runs this malware again, and then they use a command shell to execute several programs that probe what's going on in the system, and then it basically again stores that into some file, and then this file is ultimately exfiltrated using this other program called mnsend. And finally, there is a program called burnout.bat, which ends up actually removing a lot of files. So it's actually a cleanup program. So this is the kind of picture we generate. This, in fact, the example here is in fact one of the simplest attacks we detected. Here is another example. The difference here is that there is no malware that's really being downloaded and run. Instead, what happens is that the attacker downloads the malware into the memory of a running process and runs it right there. And this is a technique that attackers use because there are a lot of tools that can detect file-based malware, because when you download and store something in a file and execute the file, it's a relatively easy thing to detect. Whereas if it's downloaded directly into memory and executed right from the memory, then it's a little bit harder to detect. So that's, this example shows how that such an in-memory attack works. So there are over last few years, we had DARPA carried out 5 of these red team exercises, each of them lasting for about a couple of weeks, where students from our lab will be monitoring this data and in real time, constructing, graphs like this and reporting back to the red team, and the red team kind of, grades them and, gives them essentially a summary of how well they did. So it's kind of an interesting exercise, because it's kind of like a game, right? So you're trying to find what is going on, and so the technique we produced was quite successful, and there are a number of papers on my lab website that describes, that gives more detail about this this type of work. So to summarize, we work on vulnerability analysis, vulnerability mitigation, and basically malware containment and detecting these attack campaigns. So if you have, if you're interested in any of these things, feel free to, send me email or fix up an appointment to talk to me, and we can discuss possible research topics. So any questions at this point?